Hello Year 13, this is our last video of the entire course and it's going to cover the next few lessons. It's about two new concepts for you that kind of follow on from our stuff on lattice enthalpy. Those concepts are entropy and Gibbs free energy. We're kind of tackling why reactions happen spontaneously, what is it that enables that to happen. These are the specification points we're covering. There's quite a lot here, so pause the video if you want to see them. So let's define entropy first. Entropy is loosely defined as a measure of the disorder of a system. Solids are very ordered, gases are very disordered because the particles are freely moving everywhere. A solid, you could predict the order based on the fact that you know where all the particles are, you know how they arrange themselves. A more advanced definition of entropy talks about the number of ways something can be arranged. You can only arrange a solid really in one way, but gases you can arrange in a lot of ways because there's lots of space. And that's kind of how we quantify disorder. But what we're more interested in is knowing how to spot a positive entropy change. So for example, anything that makes more moles of gas on one side than are on the other side is going to be a positive entropy change. It's quite a big positive entropy change when you do the thermal decomposition of calcium carbonate because you make carbon dioxide gas and you start off with a solid which is very ordered. If you dissolve something in water, you make an aqueous product from a solid reactant, then that's going to be a positive entropy change. And if there's more moles of gas in the products than the reactant, so this bottom one is a negative entropy change, there is a decrease in disorder as we go across. Now, positive entropy changes are energetically favourable. We'll go into what that means in a second. So how do you calculate an entropy change? Well, the entropy change is quite easy to measure. We can know the absolute value of entropy, not like enthalpy. And it's quite simply the sum of the products times by the stoichiometric constant, so that's what the N stands for. Sum of the entropies of the products times by their stoichiometry minus the sum of the reactants entropies times by the number of moles of them. So in this reaction we have 1 mole of N2O4 in the products, so we do 1 mole times 304.29 joules, which is joules per mole per Kelvin, which is the entropy of N2O4. And we subtract from that 2, because we have 2 moles of NO2 times 240, which is the entropy of 1 mole of nitrogen dioxide. Subtract those two from each other and we find that we've got a negative entropy change, as you would expect, going from 2 moles of gas to 1 mole of gas. So, whether or not a change happens spontaneously depends on 3 things. The entropy change, whether it's positive or negative, we want a positive entropy change. The enthalpy change, whether that's positive or negative, we want a negative enthalpy change. And the temperature, and how high the temperature is. We balance all of these factors into what's called the Gibbs free energy, which is calculated as a change. The Gibbs free energy change, delta G, is equal to delta H, the enthalpy change, minus T, temperature, times by delta S, the entropy change. Enthalpy minus T, temperature, times entropy. Because if you think about it, the hotter something is, the more disordered it is because the particles move around more. If delta G is negative, the change is going to happen spontaneously. So this value predicts to us theoretically whether an experiment will a reaction will happen when we experiment. If we know what delta H and delta S are, we can also work out the minimum temperature a reaction will happen at, because that would be when delta G is 0. So if we set delta G to 0, we can find out what the temperature needs to be for a reaction to happen. Let's do that now for this reaction. So delta H is minus 57.2 kilojoules per mole. I just realised I've got the arrow the wrong way around. It should be, this is an equilibrium reaction, the arrow should be going the other way, but don't worry. So delta H is minus 57.2. Delta S, we worked out earlier, is minus 175.83. Delta G equals delta H minus T delta S. If we set that to 0, notice that I've had to divide the entropy by 1000 because the entropy was in joules per Kelvin when it needs to be in kilojoules per Kelvin. That's important. So we get 572, which rearrange it, and we end up working out the temperature to be needing to be 325.3 Kelvin to make this reaction happen. You'll see that the actual effect of entropy is quite small in these reactions because it's times by temperature, but temperature tends to be quite a large number in Kelvin. relative to the size of delta H. So it does sort of all balance around. The final thing to think about is qualitatively whether we can predict are there some reactions that always happen spontaneously. And the answer is yes. Some reactions will never happen spontaneously. If you have a positive delta H and a negative T delta S, then delta H minus T delta S is always going to be positive, because positive minus a negative is a bigger positive. Equally, if we have a negative delta H and a positive T delta S, that's always going to be negative, because a negative number minus a positive number is a more negative number. If delta H is negative, so that's favourable for delta H, and T delta S is also negative, so it's a negative entropy change, the entropy is unfavourable, then delta G is going to be negative when T is small. So this reaction will only happen at low temperatures. If delta H is positive, which is not favourable, but delta S is positive, then this will be then delta G will be negative